Hello, welcome to another heat transfer question from chapter 7. So we are given this experimental Nusselt number thingy, this approximation for Nusselt number. And we are to determine the ratio of average convection heat transfer coefficient over the entire plate. So I'm just going to rewrite what we were given. Nusselt number in the x direction is equal to 0.035 times the Reynolds number to the 0.8 times the Prandtl number to the 1/3 power. So we really care about H. So H is the Nusselt number times K over X. Well, we have, for this example, a experimental approximation for Nusselt number. So we're going to use that 0.035 times the Reynolds number to the 0.8 times the Prandtl number to the 1/3, and then we say times K over X. Well, we know what the Reynolds number is. The Reynolds number is Vx over nu, and this is all to the 0.8. But notice that there is an x on top and an x on bottom. So we can subtract those exponents and say 0.8 minus 1. So now we have this to the power of 0.8 times 0.035. I'm going to pull K out front, PR to the 1/3, and then we're left with X to the 0.8 minus 1, which is minus 0.2. And that's just rules of exponents. To make my life easier, all of this mess is constant with respect to X. So we could just call this C, because what we want is at X is equal to L. So first we have to get the average. So the average value of a function. Let's just quickly review that. Let's say we have some function. I'm going to just make it relatively simple. Let's make it a triangle. So the average value for whatever function is going to be, if this bottom is L, the average value is going to be the area divided by L. So if we have H, the area of the triangle is 1/2 LH, and then we divide by L, we get 1/2 H, which is what you would expect for the average value of a triangle. Now we can do this to get the area of a function by integrating. So if we now have an equation for h of x, we have h is equal to c times x to the minus 0.2. So the average value is going to be the integral from 0 to L, 1 over L of our function h of x dx. So x to the minus 0.2 dx. And then the c, we can pull that c out because it is a constant with respect to x. So integration rules. You add 1 to the exponent and divide by the exponent. So minus 0.2 plus 1 is 0.8. Divide by 0.8. And then we have c and L evaluated from 0 to L. At x is equal to 0, the function is just 0. So we just substitute in L into this. So we say c over L times L to the 0.8 over 0.8. Now with this L on top and bottom, we can subtract the exponents. So 0.8 minus L, or 0.8 minus 1, is minus 0.2. So c times L to the 0.2 times 0.8. So we need the ratio. So we have our function h, and we have h at x is equal to L. So h at x equal L. So what goes on top? On top, average, and then 2, the other one. So we want h on top and h of x equals L on bottom. So we're going to say c L to the minus 0.2 because we're looking at x is equal to L. Now compare that to the average value. We have c L to the minus 0.2 times 0.8. So now we're left with CL to the minus 0.2 divided by CL to the minus 0.2 times 0.8. So these cancel out. So then we're left with 1 over 0.8, which is 1.25, which is the ratio we are looking for. Boom. And that's our answer.